All right, so last thing we did for 4.5 was this example about a box where we had to cut off some corners. So we're going to go to that next page that we left open, and we're going to start the next example there. I guess it would be example 3. So let's go ahead and label our paper with example 3. Okay, so it's on page 277. I'm going to show you guys the actual word problem because it's got like a little paragraph and it's got a nice little picture to go with it. So let's read through it real quickly here, and then we'll make our own picture. Make that a little bit bigger. So we're focused on example 3. Let me slide that up a little bit so we're just focused on. There we go. So it says figure 4.5.5 off to the left here shows an offshore well. It's an oil well located at a point W that is 5 kilometers from the closest point A on a straight shoreline. All right, so that's 5 kilometers over here. Next, it says oil is to be piped from W to a shore point B that is 8 kilometers from A by piping it on a straight line underwater from W to some shore point P between A and B, and then on to B via pipe along the shoreline. So what that means is we need to get the oil from W over to B. Now, is it going to be a straight line all the way underwater? Is it going to go straight to A and then over to B? Is it going to travel along some diagonal path P to P and then to B? So is it all underwater? Is it short distance underwater and then all under land? Well, it has to do with the calculus that we're going to do in just a moment. But it says here if the cost of laying pipe is $1 million per kilometer underwater and $500,000 per kilometer over land, so it's cheaper underwater, cheaper over land, and then more expensive underwater, where should the point P be located to minimize the cost of laying the pipe? So we have some scenarios here. Is it going to be all underwater, and that's the expensive type of pipe laying, and then we have the other option where P could be here, 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 here. P could be here at A. So we go 5 kilometers and then we go 8 kilometers over here. And we can easily calculate that. Let's see, 5 kilometers at $1 million per kilometer. That's $5 million just to get straight to shore in a perpendicular fashion. And then we're going to have to go 8 kilometers at $500,000 per kilometer there. So let's see, that's $500,000 times 8 kilometers, $500,000 per kilometer. That's going to be $4 million there. So it'd be 5 million plus 4 million. It's looking like $9 million if we go straight to A and then over to B. So what we're going to need to do is minimize the cost. So we'll need a cost function. So let's get a picture going first, and then we'll see what happens from there. So for my picture, you can just follow my lead here. I'm going to draw, let's see, W is this point right up here. We're going to go straight down over to this point A. So we'll go ahead and label that A. And then we got this is going horizontally. And then we got point B that's way over here somewhere. And then we've got point P that's somewhere in here. And this is the big idea here. P can be moved left or right depending on what we think is best. So we're really trying to minimize the cost by finding the correct placement of the point P. Where should we take the oil to first? Should it go to point P here, or should point P be over here, or should point P be over there, or A, or straight to B? Maybe point P is just move that over to there. So here's what we got. We've got a distance here, X, that we don't know. We got this entire distance over here, which is 8 kilometers. Which means this distance between P and B, let me draw little arrows here. Do you know this distance? If so, go ahead and say yes. Okay, now what is it? I agree with some of you. It is 8 minus x. The whole distance was 8. If you take off x, you're left with 8 minus x. If that doesn't make sense, let's pretend like x is 2 kilometers for a second. If that's 2, this better be 6. Because they have to add to 8. In other words, 8 take away the 2 that was already used. Okay, so we have a distance here. Let's go from W straight to P. And then we'll go ahead and draw a connection between W and B as well. So it could be that we go straight to B. All right. Let's call this distance right here Z. Right along that diagonal there from W to P. We're going to call that Z. And I think we can write an expression for that right now. A little Pythagorean theorem would be nice, because we want to find that distance right there. And then we're going to incorporate the costs. So let's go ahead and write down costs. So for the costs, we have underwater, and that's going to be $1 million per kilometer. And then we got over land. It's going to be a little bit less. Not a little bit. It's half that price. It's $500,000 per kilometer. It's time to talk about some limits on x. And this can be challenging, but if you think about it, I think this might not be too difficult. So we've got this 8 all the way across. Can x be 8? If you say 8, if x is 8, I'm going to move p to the right, and then 8 minus 8 would be 0. So this piece over here from p to b shrinks down to nothing because x is growing. It becomes the 8, which is what the entire distance is from a to b. So I'm thinking 8 would be the biggest. Let's try something bigger than 8. How about 9 kilometers? If that's 9, this is 8 minus 9, which is negative, and that doesn't make sense. Okay, how about x being negative? What would that mean? If x is negative, well, you're going to go 8 minus a negative 1, for example, or 8 minus a negative 2. That's going to make this 10 kilometers. So are you going to go 10 kilometers on the ground? Is that what you're saying? You'd like to go, maybe the negative x means go left 1 kilometer. Well, that doesn't make sense. I'm not going to go from W to this point P over here. That doesn't seem to make sense. So go farther away so you can, spend more money. You're fired, right? We're trying to minimize the amount of money we spend. So that doesn't make sense. So let's talk about how 0 needs to be the smallest, because you're not going to use negatives. 8 would be the biggest, okay? Because if you do something bigger than 8, 8 minus something bigger than 8 would be negative. And then x needs to be between those. All right, so we got limits on x. Let's talk about a distance. A distance that oil will travel. Okay, stay with me here. I'm going to try to speed up a little bit because we got a lot to cover. Distance the oil will travel is going to be comprised of 2 pieces. We're going to travel from W to P, wherever P may be, and then we're going to travel from P over to B. It's going to go underwater first, then it's going to be over land. So what we need is that distance W to P, and then that distance from P to B. We can simply call that Z plus 8 minus x. Let's start with that. But we need an expression for Z. So let's go up here. We've got a little triangle. There's a 5 over here. There's an x down there, and there's a z over there. And I think we all know Pythagorean theorem well enough. We can say z squared equals, let's see, x squared plus 5 squared, which is 25. So that means z would be the square root of x squared plus 25. And that means we have a nice expression for distance that will turn into square root of x squared plus 25 plus parentheses 8 minus x. Now, we do not want to minimize the distance. That's not what they asked us to do. To minimize the distance does not minimize the cost necessarily. It might, but minimizing the distance, I'm thinking you would have to go straight line from W to B. Okay, if that's the case, it is all what? Over land or underwater? Underwater is what I hope you said, and that's the really expensive route. So we might be able to save some money if we have it head towards land and then spend some less money because it's going to be over land. I think that would make sense. So let's come up with a cost equation now. Cost, also known as C of x, we'll call it. For the distance that it is, what is the square root of x squared plus 25? Is that the distance on land or underwater? If you look back over here, you'll see it. That's underwater. So we're going to put $1 million on that one. So we're going to have $1 million times the distance z, which was the square root of x squared plus 25. Okay, it's getting complicated here. Next, we have the 8 minus x distance, which I think we can see is on land. So that means we're going to add $500,000 times the 8 minus x. At this point, we have a cost for laying the pipe underwater plus the cost for laying the pipe over ground. Now, depending on what x is, these numbers will be different, right? They will change because x is going to change as we move this point P back and forth. So we have a cost function. Let's go back to the question. We would like to minimize cost. Okay, we spoke last class about how to minimize a function, you take its derivative, you find out critical points. When is that derivative 0? When is that derivative undefined? So let's rewrite our c of x in a more derivative-ready method or format. I'm going to drop the dollar sign because I think we know that's the dollar sign there. And I'm going to go put x squared plus 25 to the 1/2 power. I think that might be a little bit easier. I'm also going to go ahead and distribute this 500,000. And let's see, 500,000 is 500,000, so that times 8 would get us 4 million. You can check my math there, but I'm pretty sure I got that one right this time. And then we're going to have minus 500,000x. Okay, a little bit easier to deal with. We don't need to do product rule over there. So next up, we're going to go take a derivative, c prime of x. Find out when that c function maxes out, or excuse me, bottoms out, because we want to minimize the cost. So here goes. It looks scary, but all we have here is a power rule. The 1/2 comes down. What's 1/2 times a 1 million? I'm hoping you said 500,000 or 500,000. Then we're going to take our x squared plus 25, reduce the power. Don't leave this blank. It needs to be negative 1/2. What do we need right here? Don't forget, we always, always, always do chain rule. What goes here? Yes, 2x. Next, what happens to the 4 million? It goes away. Gone. Next, we'll have minus 500,000. And then the x drops off. All right, let's clean this up a little bit. So our derivative, c prime of x, let's see, we can put the 500,000 times the 2. That's back to 1,000,000. Put that on the top with the x, and then we'll go back down here, and we'll say that that square root is down back on the bottom. Minus 500,000. And we want to find out when that is equal to 0. Also when it's undefined. So let's talk about undefined for a moment. Can you make this fraction have a 0 on the bottom? And hopefully you can see that that's a no. X squared plus 25 is always at least 25. And then square root of that, it will be no less than 5. So there's no way to divide by 0 here, so we got no issues with dividing by 0. So the derivative is always defined. So now when is the derivative equal to 0? Well, we can do that by just solving this equation equal to 0. I'm going to move the 500,000 to the right. We'll end up with 1,000,000 x over square root of x squared plus 25. And then I added the 500,000 over. Okay, from here, I'm going to multiply both sides by that square root of x squared plus 25. So we'll go like this and like this. That gets it off the denominator. Say bye-bye and say hello. And that gets us, what, 500,000 with the square root of x squared plus 25. And then from there, let's see here, we could make this a lot simpler if we just wanted to maybe get rid of some of those zeros. Like if I just divide everything by 500,000, not mandatory, but check out what happens if I do. I think you'll like this. This is gone. You're down to a square root of x squared plus 25. Over here you got an x, and 500,000 is exactly 500,000, so that's going to be a 2x. Little bit simpler equation to deal with now. All right, we're getting there. We're getting there. What's it been? Maybe 15 minutes? All right, let's undo the square root. How do you undo a square root? Yes, we'll square both sides. So we'll get a 4x squared equals x squared plus 25. We're going to bring the x squared to the left. We'll get a 3x squared. I'm going to fast forward a little bit. Then we get x squared equals 25 thirds. So that means x equals plus or minus 5 over square root of 3. Now, one of these makes sense. The other one does not. Think about it for a second. Don't just assume that the negative doesn't make sense. But doesn't negative make sense here? If x is negative, that's putting it over here. You don't want to go a bigger distance, so you can come back this way. So we're going to drop the negative. We're going to use x equals 5 over rad 3 because the negative doesn't make sense. Okay, at this point, we have a closed interval. Remember, we have a closed interval. We built this interval. We put 0 and 8 as our limits. So we're going to go figure out what the cost is at 0 for x, at 8 for x, and 5 over root 3 for x, and then we will be done. So a little bit of space over here. I'm going to go calculate the cost at 0. Next, I'm going to go calculate the cost at 5 over root 3. Next, we're going to calculate the cost at 8. So I've got two endpoints, and I've got a critical point. At this point, I would let the calculator do all the work. Let me show you where we're going with this. We're going back to the cost function that's up here, not the derivative, but the cost function. You can go with this form or that form. You might want to go with, well, it doesn't really matter. We're going to let the calculator do the work anyways. Let's plug in 0. We can do that quickly. What's 0 squared? 0. Add that to 25. What do you get? 25. And what's the square root of 25? And that would be 5. And 5 times a million is a million. So next, over here, we're going to plug in 0 here. You're going to get 8 minus 0, which is 8. And then that 8 times 500,000, that'll be a 4 million. So we know, just by looking at it without a calculator, we can do that work in our head. Let's do the same thing for 8. Actually, better yet, let me just tell you. I'm going to plug 5 over root 3 into my calculator. I'll show it to you. If you want to try to play along, you can. So I'm going to go 1 million square root of, let's see, ooh, this is going to be tricky. I have to square the 5 over root 3. So parentheses, 5 divided by the square root of 3, close it. Nope, nope, nope. Close that. Close the whole fraction and square it and add 25. Close that. Close, close, close. Good. And then plus 500,000, parentheses 8 minus 5 square root of 3. Ew. That doesn't look right. I think I did something wrong. I'm going to double check my work here. I think what I'll do, I think I'll be slick. 5, oh, I think I know what I did. I see it. Do you guys see it? 5 over square root of 3, and then down here I put 5 square root of 3. Let's see if that fixes it. It's supposed to be 5 divided by square root of 3. That's what it's supposed to be. All right, perfect. So it's 8330127 and 2 cents. 8330127 point. We'll just go to the nearest penny. I don't think anybody's going to pay attention to the coins. All right, we're going to go ahead and calculate with an 8 in there. Excuse me. So I can go like this. Instead of a 5 root 3, I could just change that to an 8. Let's see, and I don't really need parentheses on that. That's a little bit easier to look at. 8 squared plus 25, and then 8 minus 8. Of course, that's going to disappear. So it's really just 8 squared plus 25, and that's what I got last time. So 9,433,981 and 13 cents. 9, 4, 3, 3, 981.13. Okay, I think it's fairly obvious. We are trying to do what? Maximize or minimize? Let me give you a hint. It's cost. Minimize. Okay, very good. So do you want to use x as 0 kilometers, 8 kilometers, or 5 over rad 3 kilometers? Pick the one with the smallest dollar amount, and we are good to go. So let's answer the question. The question was, where should the point P be located to minimize the cost of laying the pipe? So let's say this. Minimum cost of, copy that mess down, 8,330,000. That is an ugly dollar sign. Let me fix that. Can I get an it's cool? Thank you. 127.02 if point P is located this far, so 5 over root 3 kilometers, get the units on there, to the right of point A in the diagram. Now, there wasn't a weather vane out there. We don't know which way is north, south, east, or west. So if you're thinking, well, that seems silly to say, you know, to the right of or to the left of, okay, how do you want to describe it? We don't know which way is north or south or east or west. So if we knew that, we would say that. All right, so there's your final answer right there. Let's make sure you give this part right here. The 5 over root 3 is the actual answer. This is a little bit of extra information right there. Okay, so backing it up, big picture. What did we do here? We found a distance function. We incorporated the costs, okay, for the different pieces. That's going to come up in some other word problems that you'll see. So we incorporated the costs of the individual pieces. So now we have a cost function. How do you maximize or minimize any function? You take a derivative, you find critical points. That was this whole process. All of this was old stuff right here. Solving an equation, right? After you've gotten a derivative, set it equal to 0, solve it. Once you've got your critical points and you've got a closed interval, you're going to go plug into the original function to figure out what the cost would be if it was 0 miles away, if it were 5 over root 3 miles away, kilometers, and if it were 8 kilometers away. Whichever one is the smallest, that's the minimum cost. All right, so we stand to save, what is that, about $670,000, like 2/3 of $1 million. I think it's worthwhile to do a little analysis like this, right? So we're going to save some money if we do this. Awesome. I'm going to go ahead and stop this video. You probably need a break. If you need to, maybe you want to have the substitute pause it right here so you can finish copying whatever you need to copy there. I'm going to go ahead and stop it for myself, and we'll come back in just a